We're fascinated by supernovae, giant stars reaching the end of their lives and detonating, creating some kind of massive remnant. And as we learn more about the universe, we are finding that they aren't simple, that there are a vast range of different kinds of supernovae that can happen. And recently, one was seen that is incredibly rare, and that is that astronomers saw this bright flash, and then shortly after that, they saw another flash. And then after they did follow-on observations, they discovered that something really interesting was going on, a kind of supernova explosion that had been predicted but not necessarily observed. So my guest today is Dr. Charlotte Angus. She's a postdoctoral researcher at Queen's University, Belfast, and worked with the Young Supernova Experiment. And Charlotte and her team were looking through Pan-STARRS survey data when they found this strange double flash. And as they looked into it, they realized that they could be looking at a pulsational pair instability supernova event. The situation where it's so hot at the core of the star that you get matter and antimatter being created and annihilating, and then you get waves of material that move off into space, and those waves can collide and give you this double explosion. And so if you want to learn more about this, enjoy this conversation with Dr. Charlotte Angus. Charlotte, you came across my radar because you and your collaborators discovered a supernova that was behaving a little bit strangely. Can you explain sort of what it is that you saw?
Yeah, so we were observing with like these telescopes in Hawaii. They're called the Pan-STARRS telescopes. And when we come back and look at the sky fairly routinely and look at the same patch of sky and just kind of look for new things that are appearing. And we first started seeing light coming from the bottom corner of this beautiful spiral galaxy. It's called NGC 2891. And we saw some new light coming from the bottom corner of this galaxy, and we were like, "Oh, there's a new supernova there." So we kind of saw it. It got brighter. It got faded. That's what generally supernova do. And then about 2 months later, we started to see light coming from the same region of the galaxy again, and we were like, "Oh, hang on, has like something come back? Is this another supernova in the same region?" And we did this little trick. It's called astrometric matching. Basically, you're just kind of checking the positions of things on the sky, and in particular where they occur within a galaxy. And we confirmed that the kind of 2 points of light were coming from the same region. So we were like, "Oh, this must be like coming from the same source." And that's how we knew we had something a little bit unusual on our hands. You don't supernova, once they're dying stars, once they're dead, they're kind of gone. They don't normally come back.
And so, I mean, you say like this isn't a thing that you were expecting. Like, has this like never been seen before, or is this very unusual? So
this is it's very unusual. It's not something we've never seen before. We sometimes see supernova that get brighter again as they kind of start fading, and that's normally because so as your star explodes, it ejects a lot of material, and sometimes that material runs into other material that the star has released earlier in its life. So that can cause it to kind of get brighter again at a later stage of the supernova, but not normally after the supernova has totally disappeared, that was what was unusual. It basically disappeared completely after the first time we saw it. And then when it reappeared, we were like, "Oh, it's got really bright again." And that kind of change in brightness was like, "Oh, that's unusual."
Okay. And so I'm sure the first thing that you and your collaborators said was, why? What's going on here?
We did a lot of why. So we spent a lot of time trying. So we firstly had to convince ourselves that this was definitely coming from the same same system, really. And we went through a lot of discussion about whether this could be sort of so stars don't form by themselves. Stars form in little clusters. And we were like, maybe you've had two stars that have exploded in the same like star forming region, and it just so happens that they died within about 60 days of each other or something like that. And we ran the maths, and the probability of that happening is incredibly low. And then we went through a whole bunch of different like scenarios. If this is coming from the same system, maybe it's two stars in a binary system. Again, the probability of having both stars explode within that kind of short time frame is incredibly small. So we came to the conclusion that this is likely the same kind of star that was undergoing something that caused it to explode again. And what we kind of came to the conclusion was that this phenomenon called pulsational pair instability was the most likely way to explain what we were seeing. So pulsational pair instability is a phenomenon that occurs in exceptionally massive stars. So stars they've got to be bigger than about 70 times the mass of the sun at their birth, but they can't be too massive. They have to be sort of up to about 150, 160 times the mass of the sun. Because this mass range of stars, they have it's like a sweet spot for building their cores. So their cores are composed largely of carbon and oxygen, while they're largely of carbon and oxygen. And that carbon and oxygen, once it reaches kind of a critical mass, it starts undergoing this phenomenon called pair production. Pair production is basically you just take a very high energy, you take a photon in the core of the star, and if you give it a lot of energy, it will spontaneously produce an electron and a positron. So
matter and antimatter.
It's converting energy into matter. And those electrons and positrons will eventually at some point find each other and annihilate. And when they do so, you're removing particles from the core of the star, which means that the core of the star will compress because you've got a drop in pressure. And as the core compresses, you start heating the core up a little bit more. And when you start heating carbon and oxygen, you start fusing it, and you fuse it at a higher rate. And this releases some energy. And it doesn't release too much energy, but it releases enough energy that it basically drives a pulse throughout your star. And that pulse basically travels outwards and strips a layer of material from the outer layer of your star, a bit like peeling a layer off an onion. And that material will float outwards as a sort of shell around your star. And the star will kind of calm down. The core will relax a little bit until the kind of temperature in the core gets hot enough again to start the process of pair production. And then the cycle will repeat. But what can happen in these stars is that the energy, so the shells are ejected at different energies, and you can have a faster moving shell following a slower moving shell. And at some point, those two shells can collide. And when they collide, they will shock ionize each other, which basically means they heat themselves up and they get very, very hot and they cool down very, very quickly. And this all happens before the star has finished its evolutionary pathway. And at some point, the core will collapse. And when the core collapses, you see something which is a little bit more like a normal supernova. And this sort of signature of a bright peak of light that appears and disappears before you see a final supernova is a key signature of these massive stars undergoing these pulsations. And we thought that this could be a potential explanation for what we were seeing with this particular supernova.
I'm sorry,
sorry.
I got a million questions, but I sort of got to dismantle this a bit. Okay, so you mentioned you need the sweet spot, 70 to 150 solar masses. And is that because the heavier ones, like the ones in the Tarantula Nebula, 200 plus times the mass of the sun, a different process takes over that causes them to detonate in a different way? That's why you're in that, because I know you get actually the it's so hot that when you hit 300 million Kelvin or whatever, really hotter in the core of the star, then they're actually starting to just dismantle atoms with the amount of radiation, in addition to this matter-antimatter production that's happening.
Yeah, so you have these kind of mass ranges where so as you say, you can have ones where things totally disintegrate. If you go above that kind of 150, 160 solar masses, you don't get pulsational pair instability, you get a pair instability supernova. So same kind of phenomenon happens where you have pair production within the core, but the energy that's released from the fusion when the core begins to kind of compress down and collapse is significant, is enough to trigger runaway thermonuclear fusion. So if you've ever heard of a type 1a supernova, so these are carbon and oxygen white dwarfs, it's like one of those, but scaled up to something that's several hundreds of times the mass of the sun. So you end up with just a runaway thermonuclear explosion and it burns through everything.
Right. And they're just gone. They blow up and there's nothing. There's no remnant, no black hole. It's over.
Yeah. They totally no remnant. But there are sweet spots in those kind of higher mass ranges where you just get direct collapse down to a black hole. And it's I can't remember the exact mass ranges off the top of my head, but there are very specific mass ranges where we predict that the kind of massive stars will have different fates.
Right. Okay. And then my other sort of question then is the way you're describing this, then you've got this, as you get this matter-antimatter production in the center of the star, and you're getting these, this change in the core, and you're getting these waves that are passing through the star, and they can overlap with each other. Is that overlap happening within the star, or is it happening sort of as shells that have been ejected from the star that are then overlapping with each other?
So it's the flash that we see is from the shells that have been ejected, so they are separate to the star. But the pulsars themselves, they can happen on different timescales. So it's all about how long it takes for your core to kind of like calm down after it's emitted a pulse, and sometimes that can happen quite quickly. And it's very dependent on the mass of the star that's undergoing the pulsars. So the bigger the star is, it undergoes fewer pulsars, but they're more energetic.
Right. And so then based on your observations, were you actually seeing a supernova, or were you just seeing multiple of these collisions, but the star is still actually there?
So we believe that the first peak of light that we saw was coming from these shells of material that are colliding. This is very much thanks to the collaboration that I work with. We were looking for young and blue objects to try and find supernova while they're very young, and because this object met our kind of selection criteria, we were able to get spectra of this event. So in the spectrum that we got, we saw lots of strong helium emission features, and these stars don't start pulsating until really they've lost their outer hydrogen envelopes, and they're ejecting the outer layers, which would be helium rich. So seeing something which is just strong helium emission told us that we had interacting, so colliding helium rich material, which is a good signature if you're looking for these colliding shells. But the second time we saw light coming from this object, the spectrum shows like broader absorption and emission features, which are indicating that you have something a bit more like a terminal explosion, so something more like a supernova. When we model this, the actual model suggests that there's a pulse which is about 30 minutes before the star undergoes its final collapse and explodes. So whether that pulse triggers the explosion is a little bit of a grey area, but we think they're distinct in that we have colliding shells and then we have collapsing star.
I mean, the lives of stars is so long, and even for these very massive stars, they're still going to last 10 million years from formation to when they detonate. And so, you're seeing this event, I forget what the gap was, but in terms of, was it days, weeks, hours,
we see the final sort of 2 months of explosions.
Yeah. So you're seeing within a couple of months, you're seeing this one flash and then you're seeing this other flash. But is it possible that this is a process that had been going on for decades, centuries, and that you just happen to catch two because we happen to have pan-stars at this point?
Yeah. So so I worked with some theorists at the University of California, and we ran through a bunch of different models to see what could have created these peaks at this exact separation with their exact brightness. And the model that we found that fit actually had a pulse 11 years before. So the star would have been about 150 times the mass of the sun, and its helium core and its would have been stripped to something which would have been a helium star of about 70 or so solar masses. Its core of carbon and oxygen would have been about 50 or so. And that core would have undergone a pulse 11 years before the final collapse of the star. But the pulse itself, it would have been quite energetic, but the amount of material that it removed we wouldn't have really detected that within the Pan-STAR survey. It would have been quite a faint little kind of hiccup. And we wouldn't have seen colliding shells because it would have been the first shell that was released. But we also ran through some other models, and we found a model which was an okay descriptor for the light curve, but that event would have undergone a pulse 125 years before 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 it exploded. So we don't have the data going back that far. And we ran through a bunch of other models, and there's a few which coincided with like the Harvard plates. So we were looking, you can actually do like searches of these kind of old plates which have been digitized to see if there was something in the galaxy. So it was all good fun, but very hard to like pin down.
Yeah. Like it just wasn't a Pan-STARRS or a Vera Rubin 100 years ago. And like, I know people found some really interesting stuff in the Harvard plates, but it's more like we checked all the stars and then we checked to see if all those stars are still there, and some of them are no longer there. Right.
Yeah.
Or vice versa. So then what do you think has been left behind?
So we believe that these pulsational pair instability events build quite heavy stellar mass black holes. So stellar mass black holes being something up to about 100 times the mass of the sun. Wow. We believe pulsational pair instability produce black holes in the kind of 40 to 50, 60 solar masses. From the model that we found fits the data, this should have produced a black hole of about 47 solar masses. Right.
And I know that there is sort of this gap above about 65 solar masses. And then at that point, there is no mechanism to make a black hole at that point. So do you think that this is a way to get to really close to that maximum black hole limit?
Yes, I think this is, I think pulsational pair instability is at the moment, the best way we know how, outside of merging smaller mass black holes, to push black holes up to that, to build a single black hole in that mass range. And then actually it'll be really interesting when the gravitational wave detector LISA comes online, because it's the mergers of these kind of black holes are going to be predominantly what it picks up.
Right. Yeah. I mean, I know this is one of the big surprises that have already come out of LIGO, that you're seeing black holes merge that are in this sort of that this shouldn't exist gap. And yet there they are, and either they're smaller black holes that have already done this dance a couple of times and reaching there, or primordial black holes, or like there's something going on here. So it's great to get that confirmation, both in gravitational waves in addition to being able to see these things, observe them. So then, I mean, I think one of the things that I know astronomers are really hoping for is to see precursors, to get a sense of because once you see the supernova, it's already destroyed the evidence of what came before. And so it's really hard to know what kind of a star it was, because now it's just this explosion. Do you think that this gives you some insights into searching for potential precursor objects to supernova?
Yes. So this collaboration I work with is called the Young Supernova Experiment, and a lot of our work is focused around trying to understand the final evolution of very, very massive stars. And so Pan-STARRS is a wonderful telescope. It takes very, very deep images. And those deep images allow you to, if you monitor very local stars for a long period of time, you might be able to see in the light curve small kind of flickers in the lead up, in the kind of weeks to months to years before explosion. We actually found one of these a few years ago. There's a supernova called 2020 TLF. And we saw some wonderful, low-level variation in the Pan-STARRS light curve in the kind of weeks to months leading up to its final explosion. And it's getting a better understanding of this kind of pre-collapse activity and how that might relate to the final explosion is really, really important for our understanding of how massive stars evolve and eventually die.
What would be your response? Let's imagine Vera Rubin comes, when Vera Rubin comes online, that feels like it's sort of the perfect instrument to make those kinds of precursor detections of stars doing funny things. And let's say that you're now okay, we're going to try to observe a precursor. What kind of resources would you want to bring to bear to analyze a star that you think is about to explode?
Oh, you always want a spectrum. If you can, a very wise person once told me that a spectrum is truth, and understanding so within a spectrum, you would be able to see that you'd be able to analyze lines in the stellar atmosphere and understand if there's any kind of winds, if there's any not directionality, but sort of asymmetries to the winds as well. You would be able to pick that up in a spectrum. And if there's also the velocities, and that all feeds into our understanding of how the outer atmosphere is kind of churning away So if you can get a spectrum, getting a spectrum in real time, really, really difficult, but that would be like the gold standard.
Right. And I mean, what would be the best instrument to do that?
So for something like, you're picking up things that are generally quite faint, unless you're looking at a very, very local star, you want high resolution. So instruments like the Keck telescope has the Elris spectrograph is a wonderfully high resolution instrument, or even something like for Vera Rubin in the south, you want to go the ESO telescopes, so the very large telescope, getting like X-shooter spectra, or even UVES in the ultraviolet, see what's happening over, which it kind of extends a bit more towards the ultraviolet, and also is incredibly high resolution. That would be beautiful.
It also sounds like Hubble. Sounds like Hubble work.
Yeah, you could do it with Hubble. So I'm all about spectral resolution. So I feel as though that, because the more resolved it is, the more like structure you can see in your line profile, and that would really inform our models for like.
So sorry, like, can you explain that then? Like with spectral resolution, are you just talking about like the aperture of your telescope to give you that resolution?
No, so it's how finely you can sample. So spectrum is taking light and splitting it up into its constituent wavelengths, and the more finely you can sample the wavelength, the more you can see sort of structure in a line profile. So when you have more diffuse material and it's heated up, it emits an emission line. And if you get sort of wiggles in, like normally you might imagine it kind of looks like a bell curve. If you're looking at something that's more like a sphere and it's sort of more of a uniform spherical surface. But if you have things that are moving with some directionality, then you end up with kind of wiggles and bumps in your lines. And seeing that kind of structure, you need to finely sample that in terms of your spectral resolution.
I see. And so like the best tool for spectral resolution is probably like the Very Large Telescope or any of the like the big observatories.
You need a big telescope to get the light in the first place, but you also need the instrument with the resolution to allow you to resolve what's going on.
So a lot of people are quite excited about Betelgeuse, and we went through this whole thing a couple of years ago where it dimmed and people were like, is this it? Is this when it's going to explode? You've got to have been watching this. People ask you to place your bets. I'm going to ask you to place your bets. How do you sort of think about Betelgeuse as a comparison to some of the other stars that you look at?
So I'll be honest, I see Betelgeuse as small fry. Like it's a big star, but it's not that massive.
It's adorable. Yeah.
Yeah. It's a wee little baby star. Like it's a massive star. It will undergo a core collapse supernova, but it is not going. It will produce. It's still got its hydrogen atmosphere. It's going to produce type 2 supernova. So a supernova we see predominantly hydrogen within the spectrum. And I'm sure when it explodes, if it explodes within our lifetimes, the astronomers will point everything at it. And I will jump on that bandwagon. But it's not going to. Honestly, it's not going to explode in our lifetimes. It's not going to explode in the next. If it's within 500,000 years, I'll eat something. Like I don't think that's going to happen.
No, I mean, is that just because there's no way to know, and we know that whatever the stage it's in, it could have 1 million years easily, and so you're picking the middle of that curve and saying it's 500,000 years, or do you think it's not displaying the kinds of activity that would, like, what would make you start to go, okay, wait a minute, something's happening here? So
I'll be honest, this is kind of a little bit out of my comfort zone, but honestly, I think our models of stellar evolution, like when we model stellar evolution, we especially with massive stars, we pick very specific points in a massive star's life to model, and we don't have the computational power and time to have modeled an entire star from birth to death. So to be able to predict exactly when a star of this mass will undergo its final explosion, everything in astronomy comes with an error bar of plus or minus something huge. It's very hard for us to know precisely when a star this big will explode, because we just don't have the models to be able to pinpoint exactly when it should explode. We can give a ballpark estimate, but ballpark is plus or minus several thousands of years.
I mean, there's been a lot of really interesting research work just in the last I've been reporting on these stories like over the last couple of months, where astronomers have been looking at the sun and using machine learning algorithms to analyze activity around sunspots and starting to get a much better prediction for when you're going to see flares, how long the coronal mass ejection is going to take to get to the Earth. And it's just a matter of letting the algorithm watch a lot of activity and then tying that to outcomes where you can go, okay, now it's starting to see the precursors. You don't necessarily know while it's working, but I guess the problem is that we don't, if we had supernova going off all around us, then you could start to watch them with that level of analysis and get some kind of result. But right now we just don't have, we don't even know which are the stars that are necessarily going to explode anytime soon.
No. And we also don't have the massive stars right in our back garden for us to analyze. We have some close by, like looking in the Large Magellanic Cloud is a great place to look for massive stars. But those stars are not so, they're not so close like the sun that we can monitor their activity with that level of detail. Probably, thankfully, I think the radiation might kill us if they're really closer. But
yeah, it's funny. I mean, I've been like studying and preparing for this conversation, and so I've been sort of reading up about a lot of massive stars, and I think it's funny because you saying Betelgeuse, it's fine, it's it's adorable. At 800 times bigger than the sun, whatever it is, I forget how many times.
It's about 8 times bigger than the sun.
Yeah. Like that's pretty great. But things like the stuff in the Tarantula Nebula, like 260 times the mass of the sun, putting up 5 million times as much energy as the sun. Like it's just bonkers what these things can do, and they're going to explode. But we don't know when they're going to explode either. So, Charlotte, what are you obsessed with right now?
So right now, I am obsessed with transients that we call tidal disruption events. So these are flares which are produced when a star wanders too close to a black hole and becomes shredded by it and partly starts to feed the black hole and produce a flare. I'm actually obsessed with these, with a particular type of tidal disruption event which repeats. So you have a star on a particular orbit which means that once the star is it's not fully shredded, it's only kind of nibbled on by the black hole. And then as the star goes back out, it will at some point be brought back close to the black hole due to the dynamic of its orbit. And that means that the black hole feeds again. And I'm very interested in those systems.
Right. And so, I mean, is that kind of what you thought you might have been looking at when you saw this double flash earlier?
No, because it happened in this big spiral galaxy, and in those kind of galaxies, the black holes are towards the center. If it had happened in a smaller galaxy where in small dwarf galaxies, sometimes they're not dynamically settled and the black hole isn't quite in the middle, that could have been a kind of candidate. But yeah, I've got a theme. I like things which appear and disappear and then reappear again.
Right. But I wonder, like, if you did have a less massive black hole, like something more like one of these sort of elusive intermediate mass black holes that aren't in the center of the galaxy, and it has had a random snack, then you could see these things not at the center of the galaxy.
Yes, absolutely true. If you have an intermediate mass black hole that's just sitting somewhere within a galaxy and the star happens to wander too close to it, you can absolutely have one of these flares. Whether you could have the dynamics to get it to repeat, unlikely, but I'm going to say not impossible, because I think with stellar dynamics anything is possible. But
I guess with these tidal disruption events, what do you think this is telling us about the way black holes accrete matter?
They allow us to probe it on, we call it human-friendly timescales. Like we get to observe the entire accretion process from disruption of the star to formation of the disk to how the jets are produced within a tidal disruption event. But they also, so in particular with these repeating partial tidal disruption events, they actually they allow us to measure properties of the black hole and test our models for how accretion works, because the black hole is staying the same in between. It eats a little bit, but the amount of material it eats is small compared to the mass of the black hole. So they're a great way to test our understanding of accretion.
Yeah, yeah. There's so few things in astronomy that you can actually watch the events unfold
Oh yeah.
in a human lifetime, as opposed to, I guess, having to find 1,000 versions of it all at different stages and try to piece together some kind of understanding of what's going on.
Yeah.
Yeah, it's all really exciting. And obviously, we're going to get a ton more thanks to Vera Rubin. So, yeah, it's great. Well, Charlotte, thank you so much for your time. Good luck getting to the bottom of this mystery and hopefully finding more of these interesting supernovae.
Yeah, well, thank you very much.
I hope you enjoyed that conversation with Dr. Charlotte Angus. Now, we had an additional part of the conversation where we talked about just survey telescopes in general and her experience working with the Pan-STARRS survey, which allows you to just wait for interesting things to happen in the universe and then you can follow on. But of course, then we talked about the great survey instrument that is coming, Vera Rubin, and how the astronomical community is preparing for what is going to be this fire hose of data and what it's like to be the kind of person who waits for interesting things to happen. With Vera Rubin, interesting things are going to be happening faster than you can stay on top of them. And so it was an interesting conversation about what we can expect to see. Now, I'm going to give you a couple of additional interviews that you might like, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Barry Lake Roofing, David Giltonet, David Matz, Dustin Cable, Greg Feely, Hudson Ward, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Michael Purcell, Paul Roebuck, Sean Sargent, Spiderstop.io, Stephen Fowler Melney, Thomas Hill Skadron, and Vlad Shiblin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. You know that I am obsessed with survey instruments, and my favorite, although now it is no longer doing science operations, is the Gaia instrument. And I got a chance to interview someone from the Gaia team and really get down into the details about how Gaia worked, why it's so successful, and really what the future might hold for survey astronomy. And so if you want to check that interview out, we'll have a link here. All right, we'll see you next time.